Hey, we're still missing a lot of people, but we'll go ahead and get started. First of all, a lot of you, well, a lot of the class have not taken the test yet. It was supposed to be taken yesterday. I went ahead and opened it till midnight tonight, but after that, it's not, you're not going to be able to get full credit. So just make sure you do that. Someone else. Also, when I put this on the update, that was probably the last easy test we'll have. From now on, all the tests are going to be straight from the AP exam. And I'll have the timing the same, so you'll get used to how much time you have per question. It's not going to be as long, but if, you know, I'm not going to give you this, I think it's 75 multiple choice questions they have on the AP exam, but if I give you 25, you'll have the same amount of time per question as you're actually taking the test. And there will be free response questions. So before the next test, we'll go over those again and how the best way to answer them is and all of that kind of thing. But they didn't really have one set up for the first test, the Unit 0. So now we're actually starting on Unit 1, and that's ecology. If you took biology last year, you got a lot of this already, and it'll be reviewed. If you took biology the year before, we were doing ecology at the end when we were running out of time, and we really didn't go into it very heavy. So depending on when you took biology, this will be more or less of a review, but we're not going to spend tons of time on the introduction to ecology. Okay, so let's go ahead and start the presentation. Very cool, Robin. So you probably know more about this than I do. So, right. Okay, ecology. So like I said, we're going to go through it really quickly because the basics of ecology you should have had already. We'll go into more depth in some of the other parts than you did in biology, obviously, since this is an AP class, but let's just get the introduction going about organisms and their environment. Okay, so ecology is the study of the interactions that take place between organisms and their environment. It explains how living organisms affect each other and the world they live in. Interesting, and when we're in class, we'll go more into the quiz prefixes. I have a quiz once a week when we're in class, and you'd learn things like logi means study of, which you probably already know, but eco means house. So this is the study of your household, basically. It's the same root as economics, which is money coming and going in from the household. So ecology is the study of where we live, basically. But more technically, how the living organisms affect each other and the world they live in. So biotic, abiotic factors all together and how they interact is ecology. A couple of words you'll need to know, and we'll use these a lot throughout the year. Habitat is the place a plant or animal lives. And niche, and you'll hear this pronounced different ways, even by scientists. Some people say niche, some say niche. I sometimes will say it both ways. Usually I'm probably going to say niche because that's how I learned it. So niche is an organism's total way of life. The way to look at it, habitat is your home, niche is your job, okay, for wildlife. So if you think of a woodpecker, its habitat is the forest or the desert, depending on the species, and the niche is they feed on insects under the barks of trees by making holes in them. They make nests and holes in trees, things like that, all the different things that they do. And we'll also talk about how if two organisms have the same niche, they will compete with each other. Okay, a couple more words. The non-living environment, abiotic factors, the non-living part of an organism's environment. So air currents, temperature, moisture, light, and soil, things that are not alive, but that are part of your environment. And they obviously affect an organism's life. Whether an area is going to have desert plants or rainforest plants is going to depend on abiotic factors. We don't have a lot of rainfall here, so that makes us a desert. It gets pretty hot here. All of that affects what organisms can live here. So living environment, biotic factors are all the living organisms that inhabit an environment. And again, back to the prefixes, A means without. So bios means life, which you should know from having taken biology. So this is without life. Anytime you put A in front of something, it means without. So like anaerobic, A or an, anaerobic, asexual, and abiotic. Biotic are the living organisms, plants, animals, bacteria, anything alive. All organisms depend on others directly or indirectly for food, shelter, reproduction, or protection. Very, very, very few organisms can live isolated. Plants don't have to eat anything, but they depend on the symbiotic fungi on their roots. They depend on the bacteria fixing nitrogen from the air, all kinds of things. And of course, animals have to eat, and animals eat living things. So there's a lot of dependence back and forth. So let me see how quick this goes. All right, well, so this is abiotic or biotic. That's definitely biotic. It's a fish, it's alive. What about that? I'm trying to figure out a better way to do this, but okay, abiotic or biotic, we're looking at the tornado. It's not alive, right? It acts like it's alive, it moves and everything, but it's just wind. Here we're looking at rocks and water. There's living things in the water and on the rocks, but the rocks and water are abiotic. What about that? That's a sponge, so it is alive. It's biotic. It looks kind of like a rock, but... All right, so let's talk about levels of organization. Ecologists have organized the interactions an organism takes part into different levels according to their complexity. So starting with the simplest, an organism, an individual living thing, and in biology you would go into the definition of life, but basically one way to look at it is they're made of cells, they use energy, they reproduce, respond to the environment, and they grow and develop. If you look at a lot of things do one or more of these, but if they don't do all of them, they're probably not alive. Here on Earth, that's a pretty easy thing to figure out, but when scientists start studying life on other planets that might be different than ours, they need to have a very good definition. So life as we know it. So if you look at crystals like salt crystals and things like that, they grow, but they're not made of cells. They don't use energy. They do reproduce. So then you get things like viruses where it gets kind of tricky because they're not made of cells, but they do reproduce, respond, grow and develop, evolve, but they can't do any of that by themselves. They can only do that by programming a cell to do it for them. So they're kind of on the hazy area of whether they're even alive or not. They can cause lots of problems, but that doesn't mean necessarily they're alive. Okay, so an organism, this is a single individual. Population. This is a group of organisms, all of the same species, which interbreed and live in the same place at the same time. So a herd of zebras may be a population. You could talk about the population of people in Farmington, New Mexico. You can talk about a population of aspen trees in Colorado or in a certain area, but it's all one species. Whenever you talk about a population, it's only one species. Then we'll use the word community a lot. Community is all the populations of species that live in the same place at the same time. So you start talking about biomes. So a desert could be a community. You could have the desert community in Farmington, New Mexico, or the rainforest community in the Amazon. But it's all the living things in that area. So here in Africa, you have the trees, the grass, the zebras, the wildebeest, the insects in the grass, everything that's alive. Then you get to ecosystem. This is the populations of plants and animals that interact with the given area, and also the abiotic components. So here we start talking about a desert ecosystem or a rainforest ecosystem. So it's basically everything in the area, and different characteristics of that can give us classifications. So far we go from organism to population to community to ecosystem. And then biosphere. That's the portion of Earth that supports life. And we keep finding that that's bigger and bigger than we ever thought it was. It seems everywhere we go, we find living things. Up in the upper reaches of the atmosphere, we've dug some of the deepest mines we've ever dug, and they found bacteria in the solid rock. So life is everywhere. That a lot of the places we've looked that we wouldn't expect to find living things, we find life of some kind. Have y'all heard the news about Venus that they've been talking about? They found chemicals in the atmosphere of Venus that on Earth are only made by living things. It's a chemical called phosphine. Anaerobic bacteria produce it here, and it doesn't last very long. So the amount of phosphine that is in the atmosphere of Venus should have vanished very quickly. So it's being replenished by something. And so far, nobody can think of anything that doesn't involve life that could have done it. Now, Venus is a terrible place on the ground, but in the upper atmosphere, there are places where the pressure and the temperature get to be pretty close to what it is here. So bacteria could live floating in the atmosphere. Whether they do or not, we don't know that yet, but it's an interesting possibility. It'd be funny if we've been spending all this time trying to find life on Mars and we find it on Venus first. And by the way, if you don't know, Venus at the surface, it's hot enough to melt lead. And the clouds are made of sulfuric acid. Not a very friendly place. Okay, so the biosphere, life is found in the air, on land, in fresh and salt water. It's the portion of Earth that supports living things, which stretches, like I said, from way up in the atmosphere to deep underground. They used to think there was no life at the bottom of the ocean, but we know now there is. 7 miles deep, there's still living things. Okay, so what would this be? Just the leopard. That, of course, is going to be an organism, right? Here you see several different species. So that's going to be a community. Here we have the plants and animals. Oh, they're just talking about the deer. So just the deer would be a population. Okay, so now we're going to talk about energy flow through the ecosystem. So the ultimate source of energy on Earth, energy from the sun, photosynthesis, which is what you hear about all the time, but also energy from inorganic molecules called chemosynthesis. I'm going to show a video. I'm hoping it will work out all right.
The Pacific Ocean.
By the way, this is Bill Nye when he's being serious and not just blipping around like he does on his TV show.
250 miles off the coast of the Galapagos Islands. In 1977, a deep-sea submarine descended over 8,000 feet. Its mission? To investigate hydrothermal activity on the ocean floor. Marine explorer Robert Ballard was aboard. He detected a dramatic change in the ocean's temperature.
You know, we were not expecting what we found. We were expecting to find water, and we had a camera inside the vehicle, but it was just taking pictures, so we didn't know what we had till we came back. We brought it up to the surface, and we processed the film, and we knew the spot where the temperature spike was, and it was like going to Disneyland. Probably one of the biggest biological discoveries ever made on Earth was made that day.
Ballard and his team were the first to see it, face to face. Hydrothermal vents. Immense chimney-like structures, several stories high, spewing hot water geysers, black with minerals and nutrients. The temperature around these deep-sea vents was a scorching 760 degrees Fahrenheit. And then...
So anybody know how the water can be 760 degrees Fahrenheit when it boils at 212 degrees?
Pressure.
Pressure. The higher the pressure, the higher the boiling point. Just like up here, we're at just over 5,000 feet, and our boiling point is considerably below 212 degrees, and maybe 210, 208, I'm not sure. But down at the bottom of the ocean, it can be much, much higher.
An astonishing sight. Life, thriving without sunlight. A biological community never seen before. An exotic garden of marine life. Species without eyes. Others resembling Triassic-era fossils, over 200 million years old.
What we totally were blown away by were these giant tube worms, some of them 8, 9, 10 feet tall. And when you cut them, they bled human-like blood. I mean, when the submarine landed, there was a squish, and red blood came up around all the portholes. And that's how eerie it was. And then to find these extremely unusual creatures living in this oasis, it had no relationship to the normal life of the deep sea. And yet here they were living in this toxic water. But yet these creatures were thriving on it. And then when we dissected, I remember we took one of these clams, and we opened it up in the first place. Whew, as soon as we opened it up, it stunk.
It was full of hydrogen sulfur.
Horrible smell.
Rotten eggs.
Yeah. And we opened it up, and then we looked, and it didn't look. It looked like beef. It was red, bright red, and it didn't have an anatomy of a clam. It was like, what happened to the clam? Someone had taken over its body, and that something was a bacterium, a tiny bacterium that had figured out over eons of time how to duplicate photosynthesis in the dark chemically through a process we now call chemosynthesis. And that was the discovery, that there was another life system on Earth that did not go by the book that you and I read, that was not living off the energy of the sun, but was living off the energy of the Earth itself. And that really opens up the ballgame, I'll say. And these bacterium, we now think are the largest mass of living things on Earth.
They're in the rocks, everywhere.
In the whole mountain range.
Under the ocean.
If you added up all the people and all the living things on land and add up all the creatures in the ocean and the few things in the sky, and you got a number, so many tons, there's more tons of biomass. We used to just think, you know, the insects rule the earth. Wrong. These bacterium.
So where are these vents?
All over the earth. They were, imagine a baseball with a seam on it. That seam begins beneath the polar ice caps, goes down through the Atlantic, into the Indian Ocean, across the Pacific. It runs around the Earth for 42,000 miles. It's the largest feature on Earth, the mid-ocean ridge, and it's underlain by literally tens of thousands of magma chambers.
Is that where life began? In the hot springs?
Well, that's what people are now thinking. The biology books that we were reading have now been thrown away.
Yeah.
And they're
When I
writing
grew
new
up,
ones.
everything, you had to be on the surface.
That's right. And you had this soup and a lightning bolt hit it and you formed all sorts of amino acids and things like that. But now what we think is that the hydrothermal vents may have been the site of life on Earth. It's also given us a new prospecting tool for searching for it elsewhere with our own solar system. We're now looking at a moon of Jupiter called Europa, which we think has an ocean. We think it has underwater volcanoes, and there should be life down there. The question is, how smart are their clams?
Did hydrothermal vents give birth to the first primitive microbes on Earth? Perhaps. But one thing is certain. Their discovery challenged long-held beliefs about the conditions necessary for creating life. And once life happened, there was no stopping it.
Hey, so did that video look, could you see it all right? Did it lag real bad or anything? Okay, so those were discovered when I was in high school in the mid to late 80s. And it was a big deal. We were very excited about it. And like they said, they keep finding more and more places like this. There's places in the ocean where methane seeps out of the ground, and there's organisms that eat the methane seeps. There's the hydrothermal vents. They find them in lots of different places where they're not dependent on the sun. I'm going to show you a little bit of this video, Vsauce, that talks about thinking about, what he's thinking about is what if the sun went out? And so these organisms are not dependent on the sun, so they could still live. So if the sun went out and the earth is frozen, is where this has gotten up to.
A year or so after the sun disappeared, Earth's oceans will have frozen over, ice all the way across. But ice is less dense than liquid water, which means that ice floats. And ice is a pretty decent insulator. So, for billions of years after the sun disappeared, liquid water could still exist at the bottom of our oceans, protected and insulated from space by miles of ice above it, and warmed by vents on the ocean floor that spew water out, superheated by Earth's interior. This would continue on Earth for a very, very long time, sun or no sun. Instead of becoming frozen and lifeless, extremophiles, like microbes that live around hydrothermal vents deep in the ocean, would be fine. They live deep in the ocean, far below the point where sunlight can penetrate, and they make energy not through photosynthesis, but via chemosynthesis, converting heat and methane and sulfur into the energy they need. They are then eaten by clams and tube worms. Extremophiles deposit minerals back into the vents, meaning that their food chain is complete. It's a circle. It's independent of the
Oh, sorry.
sun. Earthlings like them would thrive if the sun were to disappear. They would live just fine without ever knowing that the sun was gone, or honestly, without ever even knowing it existed in the first place. It's amazing to think that life here on Earth, all alone, flying through space with no sun, would kind of be fine. Far from becoming a frozen dead rock or a boring dormant seed, the Earth would be a spaceship carrying living passengers with enough geothermal heat for billions of years of life. If the sun disappeared, spaceship Earth would fly out in a straight line, covering about 30 kilometers every single second. After just 1 billion years, it will have covered 900 quadrillion kilometers, or about 100,000 light years, a trip that could potentially take it all the way across our galaxy, near thousands of stars, and nothing's to say it couldn't fall into orbit around one, thaw out, and allow its still living extremophiles to proliferate life on Earth all over again. Maybe one day developing life intelligent enough to uncover whatever is left of our lives. Maybe they could even find this very video. In which case, hi, You're welcome for this video about your planet's history and journey. And as always, thanks for watching.
Okay, so there are organisms that and ecosystems that do not start with the sun, but in general, the ones we're going to be talking about this year do. So photosynthesis, you learned about this exhaustively in biology last year. Carbon dioxide plus water plus sunlight and chlorophyll yields glucose and oxygen. Okay. And that's how it's amazing to think to me that plants basically take air, water, and sunlight and build themselves. That's all a tree is made of, is air, water, and sunlight. Okay, so this is a chemical reaction where green plants use water and carbon dioxide to store the sun's energy in glucose. The energy is stored in glucose, and the glucose is stored as starch in the plants. Later in the year, we will probably do some experiments that some of you may have done in biology, where we'll make closed ecosystems out of bottles. I had kind of an interesting one over the summer. You know, when they sent us home at spring break, I had an aquarium with water plants in it and a couple of fish, a couple of little minnows. And I didn't have anywhere to set it up at home, so I put a board over the top of it to keep the water from evaporating, left it in the window, and just left it. And when I got back, the plants and the fish were all still alive. Fish didn't get fed all summer long, and it was basically a closed ecosystem. And we're going to talk about the cycles. The plants give nutrients for the fish, and the plants gave food for the fish. It was an enclosed ecosystem. Okay, so more terms. Organisms that can make glucose during photosynthesis or chemosynthesis are called producers or autotrophs. Auto means self, so this is basically self-feeding. Remember, plants don't have to eat. Even carnivorous plants, they're catching insects not for food, not for nutrients, not for glucose like we do. They're doing it just to get missing, they're usually in soils like marshes where there's a particular nutrient that they can't get out of the soil, but you can get it from a dead bug. And that's what they're after. They're not eating for the same reason that we eat. They're basically taking them like vitamins, whereas we need it for the glucose. Producers use most of the energy they make for themselves. And this is something that a lot of people are confused about even after they took biology. Producers use photosynthesis, but they also use cellular respiration to supply the energy they need to live. So they make the glucose and then they break the glucose down to get the energy from it. It's kind of a multi-step process. It's kind of weird, but the only way living things can get energy is by breaking down glucose. And plants can get energy from the only way they can trap the energy of the sun into a form they can use is by making glucose. But they still have to break the glucose down to use that energy. So it's easy to think that plants do photosynthesis, animals do cellular respiration, but that's not the case. The plants do both. Okay? Very important to remember that. Okay, so here's the opposite, cellular respiration. Oxygen plus glucose yields water, carbon dioxide, and energy. It's the reverse of the first equation. Photosynthesis and cellular respiration are the reverses of each other. The energy that is used by producers can be passed on to organisms that cannot make their own energy. So, like I said, animals in particular have to eat. Organisms that cannot make their own energy are called consumers or heterotrophs. And in ecology, you'll usually hear the producers, consumers, biology, autotroph, heterotroph. But just you need to know both terms. Something that eats, hetero means different, so it's getting its food from something else, not from itself. Okay, consumers that eat producers to get energy are called first order or primary consumers. And these are herbivores. So the first consumers, they're the second spot on the food chain, but they're the first things that are eating other things. So the herbivores are primary consumers. Now, most of the energy the primary consumer gets from the producer is used by the consumer. Just sitting there watching me, listening to me, you are burning calories. Not a lot, not as much as you would be if you were running a race, but just sitting here, your heart's beating, you're producing heat to keep your body warm, you're thinking, which takes energy, all of those things, even just twiddling your fingers, none of that can be done without energy. So you're using a lot of the energy from your food just to be alive. Some of the energy moves into the atmosphere as heat. We are radiating heat quite a bit. If you look at a thermal camera of a warm-blooded animal, you can see they're giving off a lot of heat. Okay, some is stored in the body, about 10%. Energy that's not lost to the atmosphere or used by the consumer itself, and that's available for another consumer, which would be a predator. This is why a lot of people don't eat meat for not because for health reasons, but because they think it's, or not even because they think it's cruel to the animals, but because it's better for the planet. Because if you think about it, a cow has to eat, and only 10% of the food it eats is stored in its body, and the rest of it is used just to keep the animal alive. So an area that can raise 3 cows, you could get 10 times that much food if you grew plants. I'm not saying everybody should be a vegetarian. I'm not a vegetarian, but we do probably eat more meat than we need to, and that is harmful for the planet. We'll talk about that more as we go on. But your carbon footprint for meat is much higher than it is for corn or with some other vegetable. Okay, so a consumer that eats another consumer is called a secondary or second order consumer. Maybe a carnivore or an omnivore. Could be a predator, or also scavengers. Things that eat dead consumers are also secondary consumers. And again, just like the first time, most of the energy the secondary consumer gets is used by the secondary consumer. Some of it's lost as heat, some is stored, about 10%, and can be passed on to another consumer. This is one reason, not the only reason, because you can imagine farming carnivores would be problematic in lots of ways. But again, if you decided you wanted to eat wolves, wolves are a bad example because they're omnivorous. Mountain lions. If we decided we were going to farm mountain lions for food, now you've got to have the land to raise the food for the cows, and then the cows to feed to the mountain lion. So aside from the fact that carnivores want to eat us, and it would make it very difficult to domesticate them and farm them, they're not a very efficient food source. Very few are eaten. The only ones I can think of that are consistently eaten around the world would be like dogs, and they're omnivores. So, okay, so, and it goes on and on. A consumer that eats a consumer that already ate a consumer is called a third order or tertiary consumer. It could be a carnivore or an omnivore, maybe a predator or a scavenger. And it's not as cut and dried as this. When we get to the food webs, we'll see if you have a hawk that eats a rabbit that ate the grass, then it's only a secondary consumer. But if it eats a snake that ate a mouse that ate the plant, then it's a tertiary or third order consumer. So many animals can be in several different ones of these positions, depending on what they're eating. Because nothing, we talk about that they eat one thing, but when you look at the food webs, there's several different things they could eat. Okay, so if they eat producers and other consumers, they're called omnivores. That's us. We're omnivorous. Omni means all. Vor means to eat. So carnivores, carn means flesh. Omnivore, herb means a plant, and omni means all. So omnivores eat both plants and animals. And more terms that you probably already know. If you hunt and kill other consumers, it's a predator. The animal that is hunted and killed is called the prey. Consumers that eat other dead consumers are called scavengers. Vultures, flies, lots of things like that. The transfer of energy from the sun to the producer to primary consumer and then on to higher order consumers can be shown in a food chain. Now, this is always confusing to me and to a lot of other people. The arrows, intuitively, you would think the arrows should go this way because the bird is eating the frog, which is eating the bug. But the arrow follows the energy. So it's very important. And it's quite possible there will be questions like this on the AP exam. You've got to, if they ask you to draw the arrows, you've got to remember that the arrows follow the energy. So the arrows are always going to start at the sun and move this way. That's very confusing to me, but that's the way we do it. Food chains can show the available energy as well. We deal with this more, but remember you lose only 10% of the energy gets passed on. So if you have 1,000 units of energy in the plants, you only have 100 in the herbivores, 10 in the second level consumers, and 1 in the top level consumers. And if you think about it, this shows why we don't have as many predators as we have herbivores. Because the higher you get, the more things have to be alive for you to get your food. So this hawk that's eating the frog is eating the equivalent of lots and lots and lots of plants and lots of grasshoppers. There have to be enough grasshoppers to support the frog and then enough frogs to support the top level consumer. And if you had as many of these as you did grasshoppers, the population of the frogs would plummet and these guys would starve. So you've got, and it works out that way. You always have way more herbivores than you do predators. Okay, so here's just examples of food chains. Some of them can be very short. One of the shortest is in Antarctica, where you basically go from the sun to phytoplankton to zooplankton to whales. And that's it. You also see energy pyramids, which shows the loss of energy. The bottom of the pyramid, it's wide, it has a lot more, there's a lot more of them. There's more biomass, more actual weight of organisms, and there's more energy here. And as you go up, there's less and less. So there's not, if you weighed all the third order consumers, there wouldn't be near as much as there were plants at the bottom. Okay, and that's all we'll do for today. See if there's anything else I need to talk to you about. I think that's about it. So have a good day, stay safe, and we'll work on this more. Tomorrow there will be a simulation for you to work on, and I'm talking to technology to make sure the one I'm looking at will actually work on your computers. So be ready for that. Okay? So have a good day and stay safe.